So today I want to talk more about the Gaussian integers and the primes in the Gaussian integers. So this is a wonderful ring that we've been looking at. And what we proved 2 lectures ago is if we took the function delta of a plus bi and took it as a squared plus b squared, which is the same thing as a plus bi times a minus bi, that this ring was Euclidean with respect to this function. So z of I is a Euclidean ring with respect to delta. Hi, Tom. Francis. So these are our distinguished visitors in the back. I've already introduced you before you even came. And you're OK, because I just started, and we're going to have a quiz at 10:30. So we're talking about the Gaussian integers, a famous ring that was studied by Gauss, consisting of all complex numbers where the coefficients are not just real numbers, but integers. And on that ring, you have this function delta. And we showed that it was a Euclidean ring with respect to delta, which means that if you have any 2 elements in the Gaussian integers, alpha and beta, you can write beta as some Gaussian number times alpha plus a remainder with the size of the remainder less than the size of alpha. And using that, we deduced many consequences for the Gaussian integers. For example, the first consequence was that every ideal I in z of I is principal. So generated by a Gaussian integer with delta of alpha minimal. So you take the element in the ideal with the smallest value of delta that generates the ideal. Now we can say something else besides it being principal. If I'm going to add this also, if I is not equal to the 0 ideal, that's certainly a good ideal in the Gaussian integers because it's an ideal in any ring, then I claim the quotient of the Gaussian integers by I is a finite ring. In other words, the ideal has finite index. So I has finite index. By the way, let's just call this ring R so I don't have to keep writing the Gaussian integers. So I has finite index in R. So that's a particularly nice property of rings that isn't true in general, but is true for the normal integers. So if you have a non-trivial ideal in the normal integers, it's generated by its smallest positive integer, and z mod n is a finite ring. The same thing happens in the Gaussian integers. Always, the quotients are finite. And the proof is as follows. Assume we have some alpha, which is not 0, in I. And I have to show you that I has finite index. Well, then, alpha times alpha bar, which is this a squared plus b squared, right? I mean, this is just alpha times alpha bar. When you take complex conjugate of a number, you get that. Let's call this number. This is some number n, which is some positive integer. Because if alpha is not equal to 0, either the a coordinate or the b coordinate is non-zero. So the sum of these squares is positive, so you get some positive integer, right? And this element n is in I. Why is this integer in the ideal? If alpha is in, yeah?
Because it's product of something in the ideal.
Yeah, exactly. This is something in the ideal, and this is something in the ring. And any time you multiply something by the ideal by something in the ring, you stay in the ideal, definition of an ideal. So therefore, the ideal, whatever this ideal is, it contains the principal ideal generated by n. Because once n is in the ideal, all multiples of n are in the ideal. But I claim that this ideal has finite index in the ring. I claim that this ideal has index, finite index, n squared. And if this index is finite, then certainly this index is finite, because the size of this index is this times this. Why does this have finite index n squared? Well, what is the principal ideal generated by n? The principal ideal generated by n consists of all the things of the form na plus nbi, a, b in z, right? So the cosets of R mod n are represented by the elements a plus bi, where 0 is less than or equal to a is less than n, and 0 is less than or equal to b is less than n. Because anything can be brought into this form by adding or subtracting something of this form. Right? And they're exactly n squared cosets, because there are n possibilities for a and n possibilities for b, so they're n squared cosets, which shows that this has index n squared in this, which says that whatever this index is, it's finite. Okay? Now you might ask, what is the index? Once we know it has finite index, and we know its principal, right, can we calculate this index in terms of some quantity associated with the generator? Okay, there should be some formula for the index once it's finite. Okay, so here's the formula. In fact, if I is generated by the element alpha, then the order of R mod I is just our quantity delta of alpha, a squared plus b squared. So that's a positive number associated with any Gaussian integer, and it tells you, in fact, this Euclidean function turned out to be the index of the principal ideal in the ring. Just as it worked for the integers, if you thought about it, right? For the integers, this delta function was the absolute value of n, which is the size of the quotient ring of z by the ideal generated by n. Same thing for the Gaussian integers. All right, so before we prove this, we ought to check that it's true in one case that we already know it. We've just calculated the index of an ideal. Which ideal have we just calculated the index of? Yeah, over here. We just calculated the index of this principal ideal. Whatever this is, it's certainly a Gaussian integer. What's delta of n? N squared, because n is of the form a plus bi, where b is 0, a is equal to n. So delta of n is n squared. So at least this works when alpha is equal to n is in z. And you want to see that it works in general. By the way, I should now say to the guests, if you're totally lost, there's a really good quantitative reasoning course in Science Center D called The Magic of Numbers, which I developed for the Harvard Core. And you can go down there and you'll learn about the RSA crypto system, which is the crypto system we use to send our credit cards over the internet. So I won't be insulted if at this point you decide you'd rather go to Science Center D. Okay, I won't even look. Okay, so now let's see why it works in general. Let's write the number alpha as a complex number as r e to the I theta. Okay? Now notice that delta of alpha is the number r squared. Right? Because r is the absolute value of alpha. I should have written what delta of a plus bi is. It's a squared plus b squared. Whereas the absolute value of this complex number would be the square root of that. Right? So delta of alpha is this r squared. Now, what does the ideal alpha times I look like? Well, I'm going to draw you a little picture. Here are the elements in z of I as complex numbers. They just form the rectangular lattice, right? All integer multiples of, so here's 1 plus I, here's 2 plus I, here's I, etc. So you get this square lattice like this. Now what happens if you try to figure out which subset of these points are in alpha r? Well, you have to multiply 1 by alpha, so you get some number, maybe up here, alpha, right? And then you have to multiply I by alpha, so you get some perpendicular number up here. Let's hope it's, so this alpha seems to be here, 2 plus 2i. So if we multiply I by 2 plus 2i, we get minus 2 plus 2i, so that's over here. Let's draw it correctly. Here's alpha times I. And then you take the subgroup of the complex numbers generated by alpha and alpha times I, and that's alpha r, right? Because this is alpha times 1, and, alpha times a plus alpha times bi. So it's all multiples of alpha and all multiples of alpha I. So instead of getting this square lattice generated by 1 and I, you get a subgroup of it generated by alpha and alpha times I. Now what have you done? You've taken the lattice and you've rotated it through an angle of theta. This is the angle theta of this e to the I theta, because when you multiply by a complex number, the argument changes by theta, right? And you've scaled the lattice by the absolute value of alpha, which is r. So you've rotated through theta, and you rotate by theta, scale by r, which is the square root of delta of alpha. And then what you have to convince yourself of, and I'll leave this, it's the same argument here, where in this case we rotated by 0. Here's theta is equal to 0, and we scaled by n. And when you scale a lattice by a factor, and you're a lattice in the plane, then the sublattice you get has indexed that factor squared. So that's why this scaled lattice by r has index r squared. And that's why the index turns out to be delta of alpha. You can convince yourself of it in the following way. The volume of this basic parallelogram here, as a basic square in fact, compared to the volume of this square, is this square is r squared times the area of this square, right? When you scale by a factor in the plane, you scale the area by r squared. So it's going to take r squared of these little squares to fill it up. And they generate the cosets. If you were in a three-dimensional space, if you scale by r, you'd scale the volume by r cubed. But here it's r squared. And we've conveniently set up the delta alpha to be exactly the square of the absolute value. So that gives the index of the ideal. Artin has a nice picture of this, which may make it a little clearer. OK, so we now know that every ideal is principal. If it's non-zero, it has finite index. And this Euclidean function tells us what the index is. OK, now one other thing before the third thing we get, finite index in R equal to delta of alpha. And the second thing we got out of this was R has unique factorization into primes, because that's true of any ring in which every ideal is principal. And what that means is that an arbitrary Gaussian number can be written as a unit times prime Gaussian numbers and this is a unit, and that factorization is unique up to multiplication by a unit and rearranging the terms. In other words, the element determines the primes in its factorization. And remember what the primes are. The primes are elements such that when you take the principal ideal generated by P, it's maximal with respect to principal ideals. But in this case, every ideal is principal. So this has to be a maximal ideal. Or another way of saying it is this quotient ring is equal to a field. And since the quotient is finite, it has to be a finite field. So the primes are exactly the elements where when you divide out by that principal ideal, you get a finite field. Not a finite ring, a finite field. And any element can be uniquely factored into a unit times a product of primes. Now that sounds good, but it sounds better than it is. Because in our other rings where we had unique factorization, namely the integers or polynomials or even polynomials over the integers, we made a list of what the primes were. And we knew what the units were. If we're really going to get any power out of this theorem, we have to determine, first of all, what are the units in the ring? And then we have to have a way of describing the different primes in the ring. So we know what the building blocks are for multiplication. It's all very well to say everything factors uniquely into primes, but if you don't know what the primes are, what have you got? So let's recall that the theory for the integers, where we had the same theory, we knew that the units were plus or minus 1, and the primes were our usual prime numbers, 2, 3, 5, 7, 11, 13, 17, etc. We don't know them explicitly. In fact, the search for prime numbers is a sort of big problem in mathematics. But we know we have some list, some way of describing them among the integers. And when we had the ring of polynomials over a field, the units R star were the same as the non-zero elements in the field, were the polynomials of degree 0. And the primes, P of x, were the irreducible monic polynomials over the field. Now again, we don't have a list of the irreducible polynomials for most fields. For some fields we do. For example, for the complex numbers, an irreducible polynomial has degree 1. Right? That's the fundamental theorem of algebra, that any complex polynomial has a root. So it can only be irreducible if it has degree 1. So if, for example, f is equal to c, the irreducible polynomials are all of the form x minus alpha for alpha in c. Namely, there's a list of the primes, and they correspond to the elements of the complex numbers. For f equal to reals, the irreducible polynomials either look like x minus a real number, or they look like x squared minus rx plus s, where this is a quadratic polynomial which has no roots, namely r squared minus 4s is less than 0 by the quadratic formula. So there are two different types of primes, of degree 1 and degree 2. When you get to a complicated field, like the rational numbers, they're irreducible polynomials of every degree. And I told you that was true for the field of 2 elements. They're irreducible polynomials of every degree. So this isn't a complete description of the primes any more than this is a complete description of the primes. But at least we have some idea of what we're talking about. So that's what I want to do now for the rest of this lecture, is to take this theorem, the unique factorization in the Gaussian integers, and make it explicit by telling you what the units are and what the primes are, in the same way we have this described. Okay? So let's start with the units. So I want to make one observation about this delta function. So we have this map from delta from R to Z that takes an element alpha, and it takes it to alpha alpha bar, which is this a squared plus b squared. And so in fact, it goes to the non-negative integers, but never mind. Now that can't possibly be a ring homomorphism. Why, for example, can't it be a ring homomorphism? It cannot be a ring homomorphism. It's not additive. Very good. I mean, for example, it couldn't, I mean, this isn't even a group. So it's not a ring. I mean, the positive integers are not going to be a group because you can't subtract. So it's not a ring homomorphism, but it has the following nice property. Delta of alpha times beta is delta of alpha times delta of beta. It's multiplicative, even though it's not additive, and delta of 1 is 1, of course. So this is just because the complex absolute value is multiplicative. Namely, the absolute value of z times w squared is the absolute value of z squared times the absolute value of w squared. That's multiplication in polar coordinates. So this is true in the complex numbers. So it has nothing to do with actual arithmetic or integers or anything like that. It just has to do with a property of the complex absolute value. Good. All right, now I claim alpha is a unit implies, well, in fact, if and only if delta alpha is equal to 1. Okay, let's see why that's the case. Well, certainly if delta alpha is equal to 1, alpha is a unit. So in this direction, it says if delta alpha is equal to 1, then alpha bar is a multiplicative inverse to alpha. So that this is another element in the ring, such that when you multiply it by alpha, you get 1. On the other hand, let's go the other direction. Suppose that alpha is a unit. Well, to say alpha is a unit means that alpha times some beta is equal to 1 for some beta in the ring. Now apply delta to this. Delta alpha times delta beta, because it's multiplicative, you can take the delta of this side, it's delta of alpha times delta beta, is equal to delta of 1, which is equal to 1. So this is an integer times another integer is 1. The only way that can happen is if both of these are plus 1 or both of these are minus 1. But they can't be minus 1 because delta is positive. So that means both of these are plus 1. Okay, so what we're using here to do this if and only if is that we know what the units are in the integers. Right? We know what elements have multiplicative inverses in the integers, and this map allows us to transform the question of units in this ring to units in this ring. Okay, well, when is delta alpha equal to 1? That means that a squared plus b squared is equal to 1. That puts a pretty serious restriction on a and b, right? Because they're integers. So that means a is equal to 0 and b is equal to plus or minus 1, or a is equal to plus or minus 1 and b is equal to 0. Correct? I mean, if the sum of these squares is 1, one of them is 0 and the other one's 1. Okay, that gives 4 possibilities. So that means that alpha is equal to 1, minus 1, I, or minus I. Those are 4 units in the ring. And so we've just identified what the unit group of the ring is. R star is equal to the group 1i, I squared, I cubed is cyclic of order 4. Because I squared is minus 1 and I cubed is minus I. So in the picture that I drew you of the Gaussian numbers, the units are these, the points closest to the origin, the 4 points closest to the origin. This is delta equal 1. Then there's a little circle where delta is equal to 2. See, delta is sort of the shells of this lattice, right? Okay, so we've got the units. This is only 4 choices here. Now we have to figure out what the primes are. So the next question is, what are the primes of R? Well, let's call a prime, because I'm going to need a rational prime. Let's call a prime, let's give it an interesting, let's call it a beta. No, let's call them pi of R. Pi will be our letter for a prime here. Okay, now we know R mod pi is a finite field. And we saw previously, and I'll review the argument for you, that finite fields have a certain number of elements. What was the number of elements possible in a finite field? You guys remember? Pardon? A power of? Yeah, so good. So the order of r mod pi is equal to p to the n for some prime p in z and n greater than or equal to 1. Now, how did we prove that the order of a finite field was a power of a prime? Do you remember this? Yes, but yeah, exactly right. By looking at it as a vector space over what ring? And how did z mod pz come up? Where do we find the p? Very good. You're absolutely right. Where do we find p, the prime that comes in here? We could do this for any field, remember? If we have a field f, close. If we have a field f, we have a canonical map from any ring, right? What's our canonical map? For any ring R, we had a canonical map from another ring to R. What was that? You got it. So we have a natural map for any field from Z to the field that takes 1 to 1 in the field. That's true for any ring. In general, this thing has a kernel which is an ideal of Z. Right? Here it has to have a kernel because this field is finite. So it can't be an inclusion of the integers, which is an infinite ring, into a finite field. So it has to have a kernel. Has a kernel. The kernel of this map is an ideal, so it's a principal ideal of the integers. And that would mean that Z mod n was a subring of the field by our isomorphism theorem, right? If you divide it by the kernel, that mapped the quotient ring into the image, right? Now, I claim that forces n to be a prime if the field is finite. Why? Z mod n is not a field, but what's the problem with that? But why? But that might be okay if it didn't have inverses. I mean, maybe the inverse here is somewhere out in the field. See, it's worse. Good. This ring has 0 divide. This ring, there, if n is not a prime, then a times b is equal to 0 in Z mod n, so in F. And in a field, if you have a product which is 0, one of the elements has to be 0. Very good. So since this is a domain, n has to be a prime. So either a is equal to 0 in F or b is equal to 0 in F, which implies that n is prime. Any factorization of n, one of the elements would have to be 0 in this ring, would be divisible by n. Is a prime p. Now we're getting there. So in fact, what we have from our canonical map is an inclusion of this field into our finite field. So that's where the p came from. It comes from the kernel of the canonical map. And moreover, we know that the order is p to the n because, as Emily said, this field can be thought of now as a vector space over this field of finite dimension, and n is the dimension over Z mod pz of the field. Good? So that's what we know abstractly. If we have a prime, which is non-zero, this is a finite field, so its order is p to the n. Now, I claim we know more in this case. In this case, I claim that the dimension is 1 or 2. Nothing bigger. That's good. That's going to help. Why is that? Well, the reason that is if you think of it, what this means, the fact that under this canonical map, p is in the kernel, right? So means that in this ring, multiplication by p is 0, right? Which means that p is itself 0, has to be a multiple of pi. in R. Namely, that the prime P, which is 0 in this ring, because this is injected into this ring, but P is an element in R, it would be 0 in this ring only when it's a multiple of pi. So the ideal generated by P so P times R is contained in pi times R, which is contained in R. And this index, we've seen, is P squared. So there are only two possibilities for this index, which is the order of our finite field. It can be P squared, or it can be a number, P to the n, that divides P squared, or it could be P. So this is either P or P squared. Good? See?
I'm sorry, not quite.
Atticus. Not quite good enough. Let's go again. All right. We have this finite field that we're studying. Now I claim that the prime P, which came up in the calculation of its order because we had the canonical map of Z mod P into the field, the prime P, which is an element in R, is 0 in this quotient ring. Because what this says is that 1 plus 1 plus 1 P times is equal to 0 in this field. But this is the number P. So the prime P is 0 in this ring. Something in R is 0 in this ring if and only if it's in this ideal. The elements in this ideal are the multiples of pi. If P is a multiple of pi, then the principal ideal generated by P is contained in the principal ideal generated by pi. Namely, anything which is a multiple of P is certainly a multiple of pi. But the principal ideal generated by an integer, we saw had index n squared in the full ring. Right? This P squared is what I call delta of P. So the index of this ideal in the full ring is P squared. So the index of this ideal, which is squeezed between here and here, is either P or P squared. Good? So this is analogous to the fact that in the integers, the order of the quotient by a prime is equal to P, not P to the n. Right? There's always P to the first power in the integers. So in the Gaussian integers, you don't get all possible types of finite fields. You just get ones of order P or P squared. But we have to say which ones. OK, so now I say that there are two possibilities. And this is where the real number theory starts. And you're going to start to see why this is so much fun for the next week. There are two cases. One, R mod pi has order P squared. Then the ideal generated by pi is the same as the ideal generated by P. Because if this index is P squared and this is contained here, then this index has to be 1, which means that this ideal is the same as this ideal, which means, so pi is a unit times P, right? Or equivalently, P is itself a prime in R. Namely, the rational number P is actually a prime. If the rational number P is a prime, then this is a prime ideal, and then this ideal is prime, and the finite field has order P squared. Or R mod P is not a field, so there are non-trivial ideals pi between P and R. If it's not a field, that means there are more than two ideals, 0 and 1. So there have to be ideals between here and here, because we saw the ideals of this ring are exactly the ideals of the original ring between P and R. And these are generated phi primes with R mod pi isomorphic to Z mod PZ, namely the field of P elements. So either this has order, either P is self-prime and R mod P is a field of order P squared, or it's not a field, but there are fields between, there are ideals between P and R, and they give us new primes. So every rational prime, every one of these things, gives at least one prime of the Gaussian numbers. It either itself is a prime, or it gives primes where the residue field is of order P, and we have to figure out how many ideals we can find between PR and R that it gives. Okay? And now we also have to say which rational primes are in case 1 and which rational primes are in case 2. And then we'll be done. So this is already critical, that to any Gaussian prime we can associate a rational prime. And now we're going to make a list of which rational primes give us 1 or 2 or how many Gaussian primes we can get. So to each prime pi in Z of I, we can associate a rational prime P for every rational prime, and every rational prime is hit. Occurs. But the problem is that it might be more than it might not be a one-to-one map. There could be several ideals between P and R, and each one would give a prime in the Gaussian numbers. Okay? Now, we now try to distinguish these two cases. So the whole question really comes down to whether this ring, this finite ring, is a field. If it's a field, we just get one prime. And if it's not a field, we have to determine what are its ideals. So let's look at the ring. So study the finite ring R mod P for a rational prime P. That's our final thing to determine the primes. Okay, now this ring is the ring Z of I modulo the ideal generated by P. And I'm going to rewrite Z of I a little bit. I'll write Z of I as Z of x modulo the ideal generated by the polynomial x squared plus 1, which is what's satisfied by I. And then I have to take this ring and divide it by the ideal generated by P. Okay? This is the ring which is the abstract definition of Z of I that made no reference to the complex numbers. Remember we did that? Abstract definition. So this can also be written, since you divide out and then you divide out again, you can divide out the ring Z of x by the ideal generated by the two elements x squared plus 1 and P. Remember we showed that successive division by elements, I forget what that was called, the adjunction theorem or something. So instead of first dividing out by x squared plus 1 to get Z of I and then dividing out by P, we can just take this ring of polynomials over the integers, take the ideal, which is in principle, in fact, generated by x squared plus 1 and P, and divide. Okay? So far, so good? Now, there's nothing in this ideal that says you have to take x squared plus 1 as the first generator. You could have taken P as the first generator, and then taken x squared plus 1 as the second. So let's reverse this and say that this is the same thing as taking Z of x, dividing out by the principal ideal generated by P, and taking whatever that ring is and dividing out by the principal ideal generated by x squared plus 1. But if you take this ring, this is just polynomials over the field Z mod P. Divided out by the polynomial x squared plus 1. And this is polynomials over a field. And we saw when we took polynomials over a field and we divided out by a principal ideal when the quotient ring was a field. When was it a field? What do we need about that polynomial for this quotient ring to be a field? Exactly. This is a field precisely when this polynomial is irreducible over that field. Now we're getting somewhere. You like this? So now we're in the situation where we are in case 1 precisely when this polynomial is irreducible, and we're in case 2 precisely when this polynomial is reducible, and in fact we're going to see that the ideals between P and R in case 2 correspond to the different irreducible factors of that polynomial. Now, we only have a polynomial of degree 2. So it's irreducible provided it has no roots. Correct? Okay. So that's if and only if x squared plus 1 has no roots in Z mod PZ, which is the same thing as saying we cannot solve x squared congruent to minus 1 mod P. If we can solve this thing in the integers mod P, then this polynomial has a root and this isn't a field. All right? So let us now think about that. Let us now think about trying to solve that equation in Z mod P. So the first case I'm going to do is P equal 2. In P equal 2, if you take the polynomial x squared plus 1, it's x plus 1 squared, mod 2. Because when you square this, you get x squared plus 2x plus 1, but 2x is 0. So here the polynomial is not irreducible, and it has only one root. Yeah, x equal 1. And so in this case, you find that this is not a field, but there it turns out to be a unique ideal. In this case, there is a unique prime pi, which is the element 1 plus I, with R contains pi contains 2, and this has index 2. Because to look for an ideal between 2 and R, you'd have to find something of index 2, which would mean delta pi is equal to 2, which is a squared plus b squared. So a and b both have to be plus or minus 1, right? And there are only 4 choices for that, and they're all the same ideal, because if you take any one solution, you multiply it by a unit, you get another solution. So here's one example. Pi is equal to 1 plus I, where I took a plus 1 and b plus 1. The other 4 solutions with delta of pi equal 2 are just multiples of this by units. So for the prime 2, this polynomial was not irreducible, but there's only one ideal that's prime associated to the prime 2. Okay? If P, on the other hand, leaves a remainder of 3 on division by 4, then x squared plus 1 is irreducible mod P, and R mod P is a field. So P is prime. Why? Because if P is congruent to 3 mod 4, that means that the order of Z mod PZ star, which is P minus 1, is equal to 2 times an odd number. That's what 3 mod 4 means. Now, the element x that we're looking for, whose square would be minus 1, would be an element which would be invertible mod p and would have order 4. Right? Down here it would say x has order 4 mod p, because its square is minus 1, so if you square it again, you get to plus 1. It's order 4 in the group Z mod PZ star. And when p is congruent to 3 mod 4, you don't have any elements of order 4 in this group, because 4 doesn't divide the order of this group. The CeLO 2 subgroup has order 2. So no elements of order 4. So in particular, you can't solve, there are no roots of this equation. So for every prime congruent to 3 mod 4, there's a unique prime in the Gaussian integers, and it's just that rational prime. Okay, that's that. And finally, p is congruent to 1 mod 4. In this case, I claim that x squared plus 1 factors as x minus a, x plus a, where a squared is congruent to minus 1 mod p. Namely, we can find an element of order 4. Proof? In this case, the order of Z mod PZ star is p minus 1, which is equal to some 2 to the k times an odd number where k is greater than or equal to 2. Namely, this number is divisible by 4. Might be 8 times something, it might be 16 times something, whatever it is, it's divisible by 4. Consequently, the CeLO 2 subgroup of it has order 2 to the k. Okay, but I claim that not all elements have order 2, but the only elements of order 2 are plus or minus 1 mod p. Because if p divides a squared minus 1, that would mean it had order 2, then you factor this as a minus 1 times a plus 1. And because p is a prime and it divides this, it has to divide one of these factors. In this case, a is 1. In this case, a is minus 1. So you have a CeLO 2 subgroup of order bigger than 2, right? And there are only 2 elements of order 2, so there have to be elements of order bigger than 2, right? 4, 8, 16, whatever they are. They have to be bigger than 2. And by taking powers of those elements, you eventually get to something of order 4. Namely, if you found an element of order 4, stop. If you didn't know there was an element of order 4, but you knew there was something of order 8, then square it. That's something of order 4. If you knew there was something of order 16, take its 4th power. That is order 4. So there must be elements of order 4. So exists elements A of order 4. And if A is of order 4, so is minus A, and that factors this thing. Okay? Now, if this factors, it's not a field, so this ring is not a field. There are ideals there. And in fact, you get an ideal for every factor. So in fact, you get an ideal. This gives an ideal pi, which is generated by p and a. And this gives an ideal pi prime, which is generated by p and minus a, both primes in R. That doesn't write them as a principal ideal, but that's an ideal which is strictly bigger than the ideal generated by p. If you look at our construction of an ideal of index 5 way, way back, you'll see that we made this type of construction. Yeah. Wait a minute, let me just finish. These are both primes with R mod pi prime, both isomorphic to Z mod p. And so in this case, you get 2 primes in the Gaussian integers for every prime of the rational numbers. In this case, you get 1 prime, and in this case, you get 1 prime. And so if I were making a list of primes in the Gaussian integers, I'd have a prime here I'd have a prime here, I'd have two primes here, I'd have a prime here, I'd have a prime here, I'd have two primes here, I'd have two primes here, etc. Peter?
Do you really want x minus a, x plus a, or do you want x minus a, x minus a bar?
Here?
Yeah, I mean, for instance,
No. I want this. This is congruence mod p. A is an integer mod p.
x minus a bar, I mean, like, so for instance, the generator of, I mean,
This is-
your pi and pi prime, for instance, are identical. They're equal. Like, you want p, the thing generated by p a.
Sorry. I apologize. Sorry. Thank you. This is I minus a, and this is I plus a. Thank you. You see, in the ring Z mod p, you get an element of order 4 by sending I to a. Or you could get an element of order 4 by sending I to minus a. That's the ideal that I want. Okay? So this is the conjugate of that, if you want to write it that way. So, that's the way the Gaussian primes split up. Now, this is just the beginning of the story. This is totally cool thing that eventually will lead us to this formula. I mean, if you want to see how cool this is, consider the following sum. 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th plus a 13th. Okay? Now, that's a famous series, right? That was a series in calculus that Leibniz proved was equal to what? Pi over 4. We're going to see, and I'm going to get you here by the end of this December, that this is a theorem about the Gaussian numbers. This is a theorem that says that every ideal in the Gaussian numbers is principal. Believe it or not, that is the correct interpretation of Leibniz's identity. Now you might say, what does this thing have to do with pi and the Gaussian numbers? So you just have to relax. We're going to get there. We're getting to number theory pretty soon. But already you can see that this series is a little bit related to the Gaussian numbers because the things congruent to 1 mod 4 come with a plus sign, and the things congruent to 3 mod 4 come with a minus sign. And at least for the primes, those are the primes we've distinguished by their behavior in the Gaussian numbers. All right, so this is an identity which one can understand now in the context of number theory, which has nothing to do with calculus. Okay, next time more arithmetic.